Mars Science Laboratory is a robotic space probe mission to Mars launched by NASA on November 26, 2011, which successfully landed Curiosity, a Mars rover, in Gale Crater on August 6, 2012. The overall objectives include investigating Mars' habitability, studying its climate and geology, and collecting data for a manned mission to Mars. The rover carries a variety of scientific instruments designed by an international team. Overview. MSL successfully carried out the most accurate Martian landing of any known spacecraft, hitting a small target landing ellipse of only 7 by 20 kilometers, in the Aeolis-Palus region of Gale Crater. In the event, MSL achieved a landing 2.4 kilometers east and 400 m north of the center of the target. This location is near the mountain Aeolis Mons. The rover mission is set to explore for at least 687 Earth days over a range of 5 by 20 kilometers. The Mars Science Laboratory mission is part of NASA's Mars Exploration Program, a long-term effort for the robotic exploration of Mars that is managed by the Jet Propulsion Laboratory of California Institute of Technology. The total cost of the MSL problem is about $2.5 billion. Previous successful U.S. Mars rovers include Sojourner from the Mars Pathfinder mission and the Mars Exploration Rovers Spirit and Opportunity. Curiosity is about twice as long and 5 times as heavy as Spirit and Opportunity, and carries over 10 times the mass of scientific instruments. Goals and objectives. The MSL mission has 4 scientific goals: determine the landing site's habitability including the role of water, the study of the climate and the geology of Mars. It is also useful preparation for a future manned mission to Mars. To contribute to these goals, MSL has 8 main scientific objectives: biological, 1, determine the nature and inventory of organic carbon compounds, 2, investigate the chemical building blocks of life, 3, identify features that may represent the effects of biological processes, geological and geochemical, 4, investigate the chemical, isotopic, and mineralogical composition of the Martian surface and near-surface geological materials, 5, interpret the processes that have formed and modified rocks and soils, planetary process, 6, assess long timescale Martian atmospheric evolution processes, 7, determine present state, distribution, and cycling of water and carbon dioxide, surface radiation, 8, characterize the broad spectrum of surface radiation, including cosmic radiation, solar particle events and secondary neutrons. As part of its exploration, it also measured the radiation exposure in the interior of the spacecraft as it traveled to Mars, and it is continuing radiation measurements as it explores the surface of Mars. This data would be important for a future manned mission. About 1 year into the surface mission, and having assessed that ancient Mars could have been hospitable to microbial life, the MSL mission objectives evolved to developing predictive models for the preservation process of organic compounds and biomolecules. A branch of paleontology called taphonomy. Specifications. Spacecraft equals. The spacecraft flight system had a mass at launch of 3,893 kilograms, consisting of an Earth-Mars fueled cruise stage, the entry descent landing system including 390 kilograms of landing propellant, and 899 kilograms mobile rover with an integrated instrument package. The MSL spacecraft includes spaceflight-specific instruments, in addition to utilizing one of the rover instruments, a radiation assessment detector during the spaceflight transit to Mars. MSL EDL instrument. The MEDLI project's main objective is to measure aerothermal environments, subsurface heat shield material response, vehicle orientation, and atmospheric density for the atmospheric entry through the sensible atmosphere down to heat shield separation of the Mars Science Laboratory entry vehicle. The MEDLI instrumentation suite was installed in the heat shield of the MSL entry vehicle. The acquired data will support future Mars missions by providing measured atmospheric data to validate Mars atmosphere models and clarify the lander design margins on future Mars missions. MEDLI instrumentation consists of 3 main subsystems: MEDLI integrated sensor plugs, Mars entry atmospheric data system and the sensor support electronics. Rover equals. Curiosity rover has a mass of 899 kilograms, can travel up to 90 mph on its six-wheeled rocker bogie system, is powered by a radioisotope thermoelectric generator, and communicates in both X-band and UHF bands. Computers. The two identical onboard rover computers, called rover compute element, contain radiation-hardened memory to tolerate the extreme radiation from space and to safeguard against power-off cycles. Each computer's memory includes 256 kilobytes of EEPROM, 256 megabytes of DRAM, and 2 gigabytes of flash memory. This compares to 3 megabytes of EEPROM, 128 megabytes of DRAM, and 256 megabytes of flash memory used in the Mars exploration rovers. The Rce computers use the RAD750 CPU operating at 200 MHz. The Radial 750 CPU is capable of up to 400 MIPS, while the RAD6000 CPU is capable of up to 35 MIPS. Of the two onboard computers, one is configured as backup, and will take over in the event of problems with the main computer. The rover has an inertial measurement unit that provides 3-axis information on its position, which is used in rover navigation. The rover's computers are constantly self-monitoring to keep the rover operational, such as by regulating the rover's temperature. Activities such as taking pictures, driving, and operating the instruments are performed in a command sequence that is sent from the flight team to the rover. The rover's computers function on VxWorks, a real-time operating system from Wind River Systems. During the trip to Mars, VxWorks ran applications dedicated to the navigation and guidance phase of the mission, and also had a pre-programmed software sequence for handling the complexity of the entry-descent landing. Once landed, the applications were replaced with software for driving on the surface and performing scientific activities. Communications. Curiosity is equipped with several means of communication, for redundancy. An X-band small deep space transponder for communication directly to Earth via the NASA Deep Space Network, and a UHF electrolyte software-defined radio for communicating with Mars orbiters. The X-band system has one radio, with a 15W power amplifier, and two antennas, a low-gain omnidirectional antenna that can communicate with Earth at very low data rates, regardless of rover orientation, and a high-gain antenna that can communicate at speeds up to 32 kbits, but must be aimed. The UHF system has two radios, sharing one omnidirectional antenna. This can communicate with the Mars Reconnaissance Orbiter and 2001 Mars Odyssey Orbiter at speeds up to 2 Mbps and 256 kbits, respectively, but each orbiter is only able to communicate with Curiosity for about 8 minutes per day. The orbiters have larger antennas and more powerful radios, and can relay data to Earth faster than the rover could do directly. Therefore, most of the data returned by Curiosity is via the UHF relay links with MRO and ODY. The data returned via the communication infrastructure as implemented at Msl, and observed during the first 10 days was approximately 31 megabytes per day. Typically 225 kbit day of commands are transmitted to the rover directly from Earth, at a data rate of 1/2 kbits, during a 15-minute transmit window, while the larger volumes of data collected by the rover are returned via satellite relay. The one-way communication delay with Earth varies from 4 to 22 minutes, depending on the planet's relative positions, with 12.5 minutes being the average. At landing, telemetry was monitored by the 2001 Mars Odyssey Orbiter, Mars Reconnaissance Orbiter and ESA's Mars Express. Odyssey is capable of relaying UHF telemetry back to Earth in real time. The relay time varies with the distance between the two planets and took 13:46 minutes at the time of landing. Mobility systems. Curiosity is equipped with 6 wheels and a rocker bogie suspension, which also served as landing gear for the vehicle, unlike its smaller predecessors. The wheels are significantly larger diameter than those used on previous rovers. Each wheel has cleats and is independently actuated and geared, providing for climbing in soft sand and scrambling over rocks. The 4 corner wheels can be independently steered, allowing the vehicle to turn in place as well as execute arcing turns. Each wheel has a pattern that helps it maintain traction and leaves pattern tracks in the sandy surface of Mars. That pattern is used by onboard cameras to judge the distance traveled. The pattern itself is Morse code for JPL. Based on the center of mass, the vehicle can withstand a tilt of at least 50 degrees in any direction without overturning, but automatic sensors will limit the rover from exceeding 30-degree tilts. Instruments. The general analysis strategy begins with high-resolution cameras to look for features of interest. If a particular surface is of interest, Curiosity can vaporize a small portion of it with an infrared laser and examine the resulting spectra signature to query the rock's elemental composition. If that signature intrigues, the rover will use its long arm to swing over a microscope and an X-ray spectrometer to take a closer look. If the specimen warrants further analysis, Curiosity can drill into the boulder and deliver a powdered sample to either the SAM or the Chemin analytical laboratories inside the rover. Alpha particle X-ray spectrometer. This device can irradiate samples with alpha particles and map the spectra of X-rays that are re-emitted for determining the elemental composition of samples. Chemin. Chemin is short for chemistry and mineralogy, and it is an X-ray diffraction and X-ray fluorescence the analyzer. It will identify and quantify the minerals present in rocks and soil and thereby assess the involvement of water in their formation, deposition, or alteration. In addition, Chemin data will be useful in the search for potential mineral biosignatures, energy sources for life or indicators for past habitable environments. Sample analysis at Mars. The SAM instrument suite will analyze organics and gases from both atmospheric and solid samples. This include oxygen and carbon isotope ratios in carbon dioxide and methane in the atmosphere of Mars in order to distinguish between their geochemical or biological origin. Radiation Assessment Detector. This instrument was the first of 10 Msl instruments to be turned on. Both en route and on the planet's surface, it will characterize the broad spectrum of radiation encountered in the Martian environment. Turned on after launch, it recorded several radiation spikes caused by the Sun. On May 31, 2013, NASA scientists reported that a possible manned mission to Mars may involve a great radiation risk based on the amount of energetic particle radiation detected by the RAD on the Mars Science Laboratory while traveling from the Earth to Mars in 2011 to 2012. Dynamic albedo of neutrons, a pulse neutron source and detector for measuring hydrogen or ice and water at or near the Martian surface. On August 18, 2012, the Russian science instrument, DAN, was turned on, marking the success of a Russian-American collaboration on the surface of Mars and the first working Russian science instrument on the Martian surface since Mars 3 stopped transmitting over 40 years ago. The instrument is designed to detect subsurface water. Rover Environmental Monitoring Station, meteorological package and an ultraviolet sensor provided by Spain and Finland. It measures humidity, pressure, temperatures, wind speeds, and ultraviolet radiation. Cameras. Curiosity has 17 cameras overall. 12 engineering cameras and 5 science cameras. Msl, MADI, and Mastcam cameras were developed by Malin Space Science Systems and they all share common design components, such as onboard electronic imaging processing boxes, 1600A, 1200 CCDs, and a GB Bayer pattern filter. Mastcam. This system provides multiple spectra and true color imaging with 2 cameras. Mars Hand Lens Imager. This system consists of a camera mounted to a robotic arm on the rover, used to acquire microscopic images of rock and soil. It has white and ultraviolet LEDs for illumination. Chemcam. Chemcam is a suite of remote sensing instruments, including the first laser-induced breakdown spectroscopy system to be used for planetary science, and Curiosity Euro's 5th science camera, the remote microimager. The RMI provides black and white images at 1024A, 1024 resolution in a 0.02 radian field of view. This is approximately equivalent to a 1500 mm lens on a 35 mm camera. Mars Descent Imager. During part of the descent to the Martian surface, MADI acquired 4 color images per second, at 1600 A, 1200 pixels, with a 0.9 millisecond exposure time. Images were taken 4 times per second, starting shortly before heat shield separation at 3.7 km altitude, until a few seconds after touchdown. This provided engineering information about both the motion of the rover during the descent process, and science information about the terrain immediately surrounding the rover. NASA descoped MADI in 2007, but Malin Space Science Systems contributed it with its own resources. After landing, it could take 1.5 mm per pixel views of the surface. The first of these post-landing photos were taken by August 27, 2012. Engineering cameras. There are 12 additional cameras that support mobility, hazard avoidance cameras. The rover has a pair of black and white navigation cameras located on each of its 4 corners. These provide closed-up views of potential obstacles about to go under the wheels. Navigation cameras. The rover uses 2 pairs of black and white navigation cameras mounted on the mast to support ground navigation. These provide a longer distance view of the terrain ahead. History. NASA called for proposals for the rover's scientific instruments in April 2004, and 8 proposals were selected on December 14 of that year. Testing and design of components also began in late 2004, including Aerojet's designing of a monopropellant engine with the ability to throttle from 15 to 100% thrust with a fixed propellant inlet pressure. By November 2008, most hardware and software development was complete, and testing continued. At this point, cost overruns were approximately $400 million. In the attempts to meet the launch date, several instruments and a cache for samples were removed, and other instruments and cameras were simplified to simplify testing and integration of the rover. The next month, NASA delayed the launch to late 2011 because of inadequate testing time. Eventually, the costs for developing the rover did reach $2.47 billion. That for a rover that initially had been classified as a medium-cost mission with a maximum budget of $650 million, yet NASA still had to ask for an additional $82 million to meet the planned November launch. Between March 23 and 29, 2009, the general public ranked 9 finalist rover names through a public poll on the NASA website. On May 27, 2009, the winning name was announced to be Curiosity. The name had been submitted in an essay contest by Clara Ma, a then 6th grader from Kansas. Msl launched on an Atlas V rocket from Cape Canaveral on November 26, 2011. On January 11, 2012, the spacecraft successfully refined its trajectory with a 3-hour series of thruster engine firings, advancing the rover's landing time by about 14 hours. When Msl was launched, the program's director was Doug McQuistion of NASA's Planetary Science Division. Curiosity successfully landed in the Gale Crater at 05:17:57.3 UTC on August 6, 2012, and transmitted HAT-SAM images confirming orientation. Due to the Mars-Earth distance at the time of landing and the limited speed of radio signals, the landing was not registered on Earth for another 14 minutes. The Mars Reconnaissance Orbiter sent a photograph of Curiosity descending under its parachute, taken by its high-rise camera, during the landing procedure. 6 senior members of the Curiosity team presented a news conference a few hours after landing. They were John Grunsfeld, NASA Associate Administrator; Charles E. Lachey, Director, JPL; Peter Theisinger, MSL Project Manager; Richard Cook, MSL Deputy Project Manager; Adam Stelzer, MSL Entry, Descent and Landing Lead; and John Grotzinger, MSL Project Scientist. Landing site selection equals. Over 60 landing sites were evaluated, and by July 2011 Gale Crater was chosen. A primary goal when selecting the landing site was to identify a particular geologic environment, or set of environments, that would support microbial life. Planners looked for a site that could contribute to a wide variety of possible science objectives. They preferred a landing site with both morphologic and mineralogical evidence for past water. Furthermore, a site with spectra indicating multiple hydrated minerals was preferred. clay minerals and sulfate salts would constitute a rich site. Hematite, other iron oxides, sulfate minerals, silicate minerals, silica, and possibly chloride minerals were suggested as possible substrates for fossil preservation. Indeed, all are known to facilitate the preservation of fossil morphologies and molecules on Earth. Difficult terrain was favored for finding evidence of livable conditions, but the rover must be able to safely reach the site and drive within it. Engineering constraints called for a landing site less than 45 degrees from the Martian equator, and less than 1 kilometer above the reference datum. At the first Msl Landing Site workshop, 33 potential landing sites were identified. By the second workshop in late 2007, the list had grown to include almost 50 sites, and by the end of the workshop, the list was reduced to 6. In November 2008, project leaders at a third workshop reduced the list of these 4 landing sites. A fourth landing site workshop was held in late September 2010, and the fifth and final workshop May 16, 18, 2011. On July 22, 2011, it was announced that Gale Crater had been selected as the landing site of the Mars Science Laboratory mission. Launch Launch vehicle The Atlas V launch vehicle is capable of launching up to 7,982 kilograms to geostationary transfer orbit. The Atlas V was also used to launch the Mars Reconnaissance Orbiter and the New Horizons probe. The first and second stages, along with the solid rocket motors, were stacked on October 9, 2011 near the launch pad. The fairing containing Msl was transported to the launch pad on November 3, 2011. Launch event Msl was launched from Cape Canaveral Air Force Station Space Launch Complex 41 on November 26, 2011, at 10:02 Eastern Standard Time via the Atlas V-541 provided by United Launch Alliance. This two-stage rocket includes a 3.8 m Common Core booster powered by a single RD-180 engine, 4 solid rocket boosters, and 1 Centaur second stage with a 5 m diameter payload fairing. The NASA Launch Services Program coordinated the launch via the NASA Launch Services I contract. Cruise Cruise stage The cruise stage carried the Msl spacecraft through the void of space and delivered it to Mars. The interplanetary trip covered the distance of 352 million miles in 253 days. The cruise stage has its own miniature propulsion system, consisting of 8 thrusters using hydrazine fuel and 2 titanium tanks. It also has its own electric power system, consisting of a solar array and battery for providing continuous power. Upon reaching Mars, the spacecraft stopped spinning and a cable cutter separated the cruise stage from the inertial. Then the cruise stage was diverted into a separate trajectory into the atmosphere. In December 2012, the debris field from the cruise stage was located by the Mars Reconnaissance Orbiter. Since the initial size, velocity, density and impact angle of the hardware are known, it will provide information on impact processes on the Mars surface and atmospheric properties. Mars transfer orbit The Msl spacecraft departed Earth orbit and was inserted into a heliocentric Mars transfer orbit on November 26, 2011, shortly after launch, by the Centaur upper stage of the Atlas V launch vehicle. Prior to Centaur separation, the spacecraft was spin-stabilized at 2 rpms for attitude control during the 36,210 km/h cruise to Mars. During cruise, 8 thrusters arranged in 2 clusters were used as actuators to control spin rate and perform axial or lateral trajectory correction maneuvers. By spinning about its central axis, it maintained a stable attitude. Along the way, the cruise stage performed 4 trajectory correction maneuvers to adjust the spacecraft's path toward its landing site. Information was sent to mission controllers via 2 X-band antennas. A key task of the cruise stage was to control the temperature of all spacecraft systems and dissipate the heat generated by power sources, such as solar cells and motors, into space. In some systems, insulating blankets kept sensitive science instruments warmer than the near absolute zero temperature of space. Thermostats monitored temperatures and switched heating and cooling systems on or off as needed. Entry descent and landing. Edl spacecraft system equals. Landing a large mass on Mars is particularly challenging as the atmosphere is too thin for parachutes and aerobraking alone to be effective, while remaining thick enough to create stability and impingement problems when decelerating with rockets. Although some previous missions have used airbags to cushion the shock of landing, Curiosity rover is too heavy for this to be an option. Instead, Curiosity was set down on the Martian surface using a new high-accuracy entry, descent, and landing system that was part of the Msl spacecraft descent stage. The novel Edl system placed Curiosity within a 20 by 7 km landing ellipse, in contrast to the 150 by 20 km landing ellipse of the landing systems used by the Mars exploration rovers. The entry descent landing system differs from those used for other missions in that it does not require an interactive, ground-generated mission plan. During the entire landing phase, the vehicle acts autonomously, based on preloaded software and parameters. The Edl system was based on a Viking-derived Edl shell structure and propulsion system for a precision-guided entry and soft landing, in contrasts with the airbag landings that were used by the mid-1990s by the Mars Pathfinder and Mars Exploration Rover missions. The spacecraft employed several systems in a precise order, with the entry, descent and landing sequence broken down into 4 parts described below as the spaceflight events unfolded on August 6, 2012. Edl event August 6, 2012 . Despite its late hour, particularly on the east coast of the United States, the landing generated significant public interest. 3.2 million watched the landing live, with most watching online instead of on television via NASA TV or cable news networks covering the event live. The final landing place for the rover was less than 2.4 kilometers from its target after a 563,270,400 kilometers journey. In addition to streaming and traditional video viewing, JPL made Eyes on the Solar System, a three-dimensional real-time simulation of entry, descent and landing based on real data. Curiosity's touchdown time as represented in the software, based on JPL predictions, was less than 1 second different than reality. The Edl phase of the Msl spaceflight mission to Mars took only 7 minutes and unfolded automatically, as programmed by JPL engineers in advance, in a precise order, with the entry, descent and landing sequence occurring in 4 distinct event phases. Guided entry. Precision-guided entry made use of onboard computing ability to steer itself toward the predetermined landing site, improving landing accuracy from a range of hundreds of kilometers to 20 kilometers. This capability helped remove some of the uncertainties of landing hazards that might be present in larger landing ellipses. Steering was achieved by the combined use of thrusters and ejectable balance masses. The ejectable balance masses shift the capsule center of mass, enabling generation of a lift vector during the atmospheric phase. A navigation computer integrated the measurements to estimate the position and attitude of the capsule that generated automated torque commands. This was the first planetary mission to use precision landing techniques. The rover was folded up within an Edl shell that protected it during the travel through space and during the atmospheric entry at Mars. 10 minutes before atmospheric entry, the Edl shell separated from the cruise stage that provided power, communications and propulsion during the long flight to Mars. 1 minute after separation from the cruise stage, thrusters on the Edl shell fired to cancel out the spacecraft's 2 p.m. rotation and achieved an orientation with the heat shield facing Mars in preparation for atmospheric entry. The heat shield is made of phenolic impregnated carbon ablator. The 4.5 m diameter heat shield, which is the largest heat shield ever flown in space, reduced the velocity of the spacecraft by ablation against the Martian atmosphere, from the atmospheric interface velocity of approximately 5.8 km per second down to approximately 470 meters per second, where parachute deployment was possible about 4 minutes later. 1 minute and 15 seconds after entry, the heat shield experienced peak temperatures of up to 2090 degrees Celsius as atmospheric pressure converted kinetic energy into heat. 10 seconds after peak heating, that deceleration peaked out at 15 G. Much of the reduction of the landing precision error was accomplished by an entry guidance algorithm, derived from the algorithm used for guidance of the Apollo command modules returning to Earth in the Apollo program. This guidance uses the lifting force experienced by the shell to fly out any detected error in range and thereby arrive at the targeted landing site. In order for the shell to have lift, its center of mass is offset from the axial center line that results in an off-center trim angle in atmospheric flight. This is accomplished by a series of ejectable ballast masses consisting of two 75 kg tungsten weights that were jettisoned minutes before atmospheric entry. The lift vector was controlled by 4 sets of 2 reaction control system thrusters that produced approximately 500 N of thrust per pair. This ability to change the pointing of the direction of lift allowed the spacecraft to react to the ambient environment, and steer toward the landing zone. Prior to parachute deployment, the entry vehicle ejected more ballast mass consisting of 6 25 kg tungsten weights such that the center of gravity offset was removed. Parachute descent. When the entry phase was complete and the capsule slowed to Mach 1.7 or 578 meters per second and at about 10 kilometers, the supersonic parachute deployed, as was done by previous landers such as Viking, Mars Pathfinder and the Mars Exploration rovers. The parachute has 80 suspension lines, is over 50 meters long, and is about 16 meters in diameter. Capable of being deployed at Mach 2.2, the parachute can generate up to 289 kilonewtons of drag force in the Martian atmosphere. After the parachute was deployed, the heat shield separated and fell away. A camera beneath the rover acquired about 5 frames per second below 3.7 kilometers during a period of about 2 minutes until the rover's sensors confirmed successful landing. The Mars Reconnaissance Orbiter team were able to acquire an image of the Msl descending under the parachute. Powered descent. Following the parachute braking, at about 1.8 kilometers altitude, still traveling at about 100 meters per second, the rover and descent stage dropped out of the shell. The descent stage is a platform above the rover with 8 variable thrust monopropellant hydrazine rocket thrusters on arms extending around this platform to slow the descent. Each rocket thruster, called a Mars lander engine, produces 400 to 3,100 N of thrust and were derived from those used on the Viking landers. A radar altimeter measured altitude and velocity, feeding data to the rover's flight computer. Meanwhile, the rover transformed from its stowed flight configuration to a landing configuration while being lowered beneath the descent stage by the Sky Crane system. Sky Crane. For several reasons, a different landing system was chosen for Msl compared to previous Mars landers and rovers. Curiosity was considered too heavy to use the airbag landing system as used on the Mars Pathfinder and Mars Exploration rovers. A legged lander approach would have caused several design problems. It would have needed to have engines high enough above the ground when landing not to form a dust cloud that could damage the rover's instruments. This would have required long landing legs that would need to have significant width to keep the center of gravity low. A legged lander would have also required ramps so the rover could drive down to the surface, which would have incurred extra risk to the mission on the chance rocks or tilt would prevent Curiosity from being able to drive off the lander successfully. Faced with these challenges, the Msl engineers came up with a novel alternative solution, the Sky Crane. The Sky Crane system lowered the rover with a 7.6 m tether to a soft landing wheels down on the surface of Mars. This system consists of a bridle lowering the rover on 3 nylon tethers and an electrical cable carrying information and power between the descent stage and rover. As the support and data cables unreeled, the rover's 6 motorized wheels snapped into position. At roughly 7.5 m below the descent stage, the Sky Crane system slowed to a halt and the rover touched down. After the rover touched down, it waited 2 seconds to confirm that it was on solid ground by detecting the weight on the wheels and fired several pyros activating cable cutters on the bridle and umbilical cords to free itself from the descent stage. The descent stage flew away to a crash landing 650 m away. The Sky Crane concept had never been used in missions before. Landing site Gale Crater as the Msl landing site. Within Gale Crater is a mountain, named Rce Mons, of layered rocks, rising about 5.5 kilometers above the crater floor, that Curiosity will investigate. The landing site is a smooth region in Yellowknife Quad 51 of Rce Palus inside the crater in front of the mountain. The target landing site location was an elliptical area 20 by 7 kilometers. Gale Crater's diameter is 154 kilometers. The landing location for the rover was less than 2.4 kilometers from the center of the planned landing ellipse, after a 563 million kilometers journey. NASA named the rover landing site Bradbury Landing on Sol 16, August 22, 2012. According to NASA, an estimated 20,000 to 40,000 heat-resistant bacterial spores were on Curiosity at launch, and as much as 1,000 times that number may not have been counted. Media =videos =images . See also. References. Further reading, M.K. Lockwood. Introduction, Mars Science Laboratory, The Next Generation of Mars Landers and the following 13 articles. Journal of Spacecraft and Rockets 43, 257 Euro 257. Bibcode, 2006 JSPRO 43-257 LDOI, 10.2514/1.20678. Grotzinger, J.P. Crisp, J. Valsavada, A.R. Anderson, R.C. Baker, C.J. Barry, R. Blake, D.F. Conrad, P. Edlet, K.S. Ferdusky, B. Gillett, R. Gilbert, J.B. Golombek, M. Garcubed Meselvira, J. Hassler, D.M. Janjura, L. Lichvok, M. Mayafi, P. Markey, J. Mayer, M. Malin, M.C. Mitrofanov, I. Simmons, J.J. Bannerman, D. Welch, R.V. Yanes, R.C. Mars Science Laboratory Mission and Science Investigation. Space Science Reviews 170, 5. Bibcode, 2012 SSV 170, 5G DOI, 10.1007 per second 11214-012-9892-2. A Euro overview article about the Msl Landing Site and instrumentation. External links, Msl homepage, scientific publications by Msl team members, Msl Euro Media Press Kit, Image Gallery, Msl Euro NASA JPL News Channel videos, Msl Euro Entry, Descent and Landing a Euro Animated Video, Msl Euro NASA Updates a Euro Replay Anytime, Msl Euro Curiosity Lands a Euro NASA JPL, Video, Descent Video Sim and Real Narrated, Msl Real Time /25 FPS, All/4 FP, High Rise, Msl a Euro Landing, Msl a Euro Landing Site a Euro Gale Crater a Euro Animated Narrated Video, Msl a Euro Mission Summary a Euro Animated Extended Video, Msl Curiosity Launch NASA Kennedy, Video, Msl a Euro NASA JPL Virtual Tour a Euro Rover. Msl a Euro Entry, Descent and Landing a Euro Timeline E, Msl a Euro Entry, Descent and Landing a Euro Description. Msl a Euro Pre-Launch Preparations at KSC, Mars Science Laboratory on Twitter, Msl a Euro Raw Images, listing by JPL.